Welcome to lecture number 2 of the course Solid Mechanics. The topic is units in solid mechanics. So before going to the main topics in solid mechanics, we should know what are the common units used in solid mechanics. So we will see basic units as well as derived units. First we will see what are the basic SI units used in solid mechanics. When the physical quantity is length, then we know that SI unit is meter, small m. For mass, kilogram, small k, small g. Time, second. Force, it is in Newton. Temperature, in Kelvin. These are the basic units. Then length is used for diameter of a shaft, thickness of a plate, etc. For that measurement we are using the term length in meters. Then mass. Mass represents the amount of matter in an object. It is also used when calculating weight and inertia. So for inertia as well as weight, mass is there. Then time is an important thing in dynamic problems and impact loading. Time in seconds. Then force. The most fundamental quantity in solid mechanics is force. External force causes internal stresses and deformation. In detail we will study in the coming classes. So force is the most fundamental quantity. Its unit is Newton. And temperature is used when studying thermal expansion and thermal stresses. So once these basic units are understood, we can derive all the engineering quantities used in solid mechanics such as stress, strain, pressure, torque and Young's modulus. Some more quantities are there, we will see that. Here, derived SI units used in solid mechanics. Many derived units are there. Area, it is meter square, that is derived from m, meter, length into length, or m into m. Then volume, it is meter cube, and in the last column it is shown how it is derived. Velocity, symbol is small v, unit is meter per second. So velocity, we know that it is distance by time. So meter, unit of distance, divided by second, that is a unit of time. So meter by time, that is meter per second. Then acceleration, meter per second square. Force, Newton. Newton is derived from kilogram meter per second square. We know that F is equal to ma. Mass into acceleration. Unit of mass is kilogram. Acceleration is meter per second square. So kilogram, 1 kilogram meter per second square is known as 1 Newton. Then pressure. Pressure, the unit is Newton per meter square. Force acting per unit area is known as pressure. So force unit is Newton, area unit is meter square. So Newton per meter square is the unit of pressure. 1 Newton per meter square is known as 1 Pascal. So usually we say Pascal. And stress. Stress, many types of stresses are there. Commonly we say stress as normal stress. Its symbol is sigma. And stress is also having the same unit as that of pressure, that is Newton per meter square. So usually 1 Pascal is very small usually, so we use megapascal, gigapascal, like that, bigger units. And density, the symbol is rho, and mass by volume is known as density. Unit of mass is kilogram, so volume is meter cube, we already studied. So kilogram per meter cube is the unit of density. Then work or energy, symbol is W or E, sometimes capital E is used, and its unit is joule. 1 joule means Newton meter. Force into distance, displacement, or displacement, force into displacement is known as work. Then force unit is Newton, displacement unit is meter. So Newton meter, 1 Newton meter is known as 1 joule. That is the unit of work as well as energy. Then power. Power means what? It is the work per second. Work done per second is known as power. So its unit is joule per second. And 1 joule per second is known as watt. So thus we can say derived units are formed by combining two or more basic SI units through mathematical relationships. These units are widely used in engineering calculations, and there are many more additional derived units in solid mechanics, and we can see one by one. For moment or bending moment, the symbol is capital M. Moment is force into distance, and the unit is same as joule, that is Newton meter. Work's unit is Newton meter, so it is same as moment unit is also Newton meter, but we don't say joule. And torque has the torque or twisting moment. It is also derived from force into distance, so the same unit Newton meter, we will say 10 Newton meter or 100 Newton meter, like that. Then shear force, since it is a force, same unit like force, capital N is the symbol used, kilogram meter per second square, that is Newton. And Young's modulus is capital E in solid mechanics, and it has got the same unit as that of pressure, Newton per meter square. So in SI units we can use the same term, that is Pascal or gigapascal. And shear modulus, that is also has the same unit, Pascal, gigapascal, megapascal, like that. Then bulk modulus, same Pascal. And modulus of rigidity, that is also, it is other name of shear modulus, that is also Pascal. And Poisson's ratio is, since it is a ratio, that is meter per meter, so it is a dimensionless quantity. And strain is also a ratio, change in length by original length, so it is also a dimensionless quantity. Some more additional derived units are shown here. Shear strain, all the strains are dimensionless quantity, so no unit. Angular displacement radians, area moment of inertia, symbol is I, and its unit is meter raised to 4. So it is derived from length raised to 4. Unit of length is meter. And polar moment of inertia, the symbol is J, and it is also meter raised to 4. Section modulus, capital Z, that is meter cube. The formula for section modulus is I by Y, that we will study later. Radius of gyration, small k, since it is a radius, unit is meter. Distributed load, small w, that is Newton per meter. Load unit is force, since it is per meter, force by length, that is Newton per meter. Then surface load or pressure load, that is force per area, that is the formula, so Newton per meter square, surface load. Linear mass density, that is mass by length, so it is kilogram per meter. Volumetric strain, like shear strain or tensile strain, it's a dimensionless quantity because it is ratio of two volumes, change in volume by original volume. Now we will see common engineering prefixes. Prefix kilo, symbol is small k, then its value is 10 raised to 3. If it is mega, capital M is used, that is 10 raised to 6. Giga, capital G, that means 10 raised to 9. For example, gigapascal means 10 raised to 9 pascal. Megapascal means 10 raised to 6 pascal. Kilopascal means 10 raised to 3 pascal. Then small values like milli, small m is used, that is 10 raised to minus 3. Micro, mu is the symbol used, 10 raised to minus 6. Nano, small n, 10 raised to minus 9. So these are some of the common prefixes used. Then unit conversions used frequently in solid mechanics. So 1 kilonewton means, kilo we know that it is 10 raised to 3, that is 1000. So 1000 Newton. 1 megapascal. Mega means 10 raised to 6, so 10 raised to 6 pascal. Also, since 1 pascal is 1 Newton per meter square, when we convert 1 megapascal, then we will get another value, that is 1 Newton per millimeter square, because 1 meter is 10 raised to minus 3, 10 raised to 3 millimeter. So when 10 raised to 3 whole square, when it goes on top of the division line, it will become 10 raised to 6. So 10 raised to 6 Newton per meter square, that is 10 raised to 6 pascal. So 1 megapascal equal to 1 Newton per millimeter square. This conversion we need always in many of the problems we are going to do. And 1 gigapascal is equal to 1000 megapascal. 1 meter, 1000 millimeter, 1 meter square, 10 raised to 6 millimeter square, and 1 meter raised to 4 is 10 raised to 12 millimeter raised to 4. So we need these kind of conversions in the coming chapters. So this is all about units in solid mechanics. Some more units are there that we will study when we study the corresponding topics. If you haven't subscribed yet to this channel, please subscribe by clicking the logo on top right corner, and also click notifications so that you will get the coming topics without any delay. Thank you.